Okay, good afternoon. I apologize that I'm not here today, um, but what you are going to learn today while I'm not here is um, you're going to kind of put everything that we've talked about projectile motion together. So you need two things on your desk right now. You need, well, three things actually. You need projectiles number one, you need your notebook, you need a calculator. So if you need any of those things, have all three of them on your desk because we're going to be referring to them. So let's just start first of all with what we know about projectiles, right? So we started, before break, we started with the idea that a vector, which is a measurement that has magnitude and direction, a vector, when you're in two dimensions, you have to, it's a little bit more difficult than when you're in one dimension. And in order to have a magnitude or direction, we say the magnitude is how long the vector is, the direction is its angle. And then we call this vector that points in both the x and y direction, we call that a resultant. And we can break the resultant up into its x component and y components. So we talked about that first. Then we talked about how you can explain projectile motion, which is an object thrown at an angle. You can explain it by looking at what happens to the x and y velocity of a projectile. And we said the x velocity stays constant, the y velocity changes, and at the top the y velocity is 0, and that's what kind of traces the curved path of a projectile. And then since we drew all these triangles here, what we were doing last time I saw you yesterday is we talked about a little bit of trigonometry. And particularly we said there are two types of problems that we might solve. We call them type 1 and type 2 problems. In a type 1 problem, if you know Vx and Vy, you use these two equations to find the magnitude and direction. If you know the magnitude and direction, you use these two equations to find the Vx and the Vy. So what I want to do today is I want to put all of it together. And that's what Projectiles 1 is going to do. It's going to put all of this together. Now, if you recall, I said that I think this is the hardest unit of the year. What I hope you see when you're doing this is that when I say that it's the hardest unit of the year, every little piece is not hard. You just have to pay attention to detail when you kind of string all the pieces together. And that's what we're going to do today. We're going to string all the pieces together. You'll notice the page front in front of you in question number 1. This is all problem number 1. Right? But I always break it down into steps, and each step is something that you have seen before. Right? We are just now going to string them all together. So let's look at our first thing. So I want you to have this out, and then in a minute I'm going to ask you to use these type 1, type 2 equations that we did yesterday. So have that off to the side on your desk, and have your calculator handy. All right, let's read problem number 1. So problem number 1 is a swallow is carrying a coconut horizontally across the ground with an airspeed velocity of 11 meters per second. Suddenly, the bird loses his grip on the husk, and it falls to the ground, and it hits the ground after 2.5 seconds. All right. So the first thing we're going to do, the first thing I'm always going to ask you to do, is to draw a diagram of the situation and write down the knowns and unknowns. Now, as we've said before, when we're doing diagrams, I'm not after artistic perfection. I'm just after something that gets the idea across. And so here's what I'm going to do. I've got a swallow carrying a coconut along the ground. So here I'm going to draw that. Here's my swallow carrying a coconut along the ground, or along the in the air, going this way at 11 meters per second. Now let's think about what's going to happen when the coconut falls. So when the coconut falls, think about which direction it's going to go. If I'm going 11 meters per second, is it going to go straight down? No. What it's going to do is it's going to do the projectile thing that we have seen before, right? It's going to be kind of like the second half of this motion, right? If it's going 11 meters per second at the top, it's going to fall like this in a curve. So I'm going to draw that curve. Now, when I ask for a diagram, this is what I'm after. I want you to see the projectile. I want to see the projectile. I want to see the any measurements labeled, and then I want to see the path the projectile is taking. That's the diagram. might, just to make it totally complete, I might just draw the ground here. All right, so that's my diagram. The next thing it says to do is to write down the knowns and unknowns. Now, what's different, you've done knowns and unknowns. I mean, we've been doing that since almost the beginning of the year. You know what I mean by knowns and unknowns. But the new thing here is if you have, if you're in 2 dimensions, we have to separate our knowns and unknowns out. So whenever we do our knowns and unknowns, I have us make a T-chart here, where we put everything we know about the x direction on this side, everything we know about the y direction on that side. All right, let's look at our problem and see what knowns and unknowns we can get from this. So the one I've drawn in my diagram is 11 meters per second. So the first thing I want you to ask is, this 11 meters per second that I've drawn, is it an x direction or a y direction? Well, horizontal is x. So I'm going to say 11 meters per second is an x number. And what does it mean in the x direction? Well, it means it's a velocity. And it's velocity here at the beginning of the picture, so I'm going to call it a VI. All right. What else does the problem give me? The other thing the problem gives me is this, the 2.5 seconds. I want you to think about time. If I say it takes 2.5 seconds for the coconut to fall to the ground, am I talking about the x direction and the y direction, or the y direction? And this turns out to be a trick question, because time is not a vector, time is a scalar. And because time is a scalar, it doesn't have direction. It's the same for the whole problem. And so whenever we have the time, I write the time on both sides of my T-chart. All right. And there's another thing we know. We know the acceleration of gravity, right? Gravity pulls these things down. And you, just like in previous problems, you have the option to decide which way is the positive acceleration. This time I'll go ahead and say that down is the positive direction. So if I do that, what I'm saying is that my acceleration, which is going up and down in the y direction, right? The acceleration here we said is positive 9.8 meters per second squared. What is the acceleration in the x direction? Well, if you recall, we said that the x velocity stays constant. Constant velocity is like saying 0 acceleration. These two things here, this a equals 0 and a equals 9.8, those are going to be true for every problem. Those are actually the first knowns and unknowns I would usually do, because they're true for every problem. Because gravity only points down in the y direction. It does not point in the x direction. All right, what else? There's one other thing we know. Let's look back at our notes to figure out what it is. What else do we know? Well, we know that at the top, the y velocity is 0. So the top here comes at the beginning of the motion, so I'm going to say that my VI in the y direction is 0. All right. I think that's all that we know at this point in time. Those are the only things that we know. So we're done with our knowns and unknowns. But notice that whenever we do our knowns and unknowns, we want to separate them out like this in a T-chart. All right. Now, for the rest of it, the fact that we separate these out into x and y is important, because for almost the rest of this problem, what we need to do is, for each part, we want to limit ourselves to looking either at the x or the y, but not both. So let me give you an example of what I mean. If I say, how high was the swallow flying? Well, if I'm saying how high, is that a question about the x dimension or the y dimension? Well, height is up and down, so I'm going to say that's a question about the y dimension. And to remind me of this, I'm just going to make a mark here that for this problem, I'm talking about y. All right. And if I want to know how high the swallow is flying, what would that be? Well, height is kind of like a vertical distance, so I'm looking for distance. So the idea here is I want to find an equation. I want to find distance using only y numbers. Now we're going to look at our Old Faithful Big Chalupa Ain't Got No Time on the bulletin board over there. Right. So if I'm looking at y numbers, I know VI, T, A, and I want to find D. So which equation over there has VI, T, D, and A? Take a look. Try and decide. Tell your partner. I'm going to stop for 10 seconds for you to tell your partner. And you should have told your partner that the one that has all these in it is Big Chalupa. So I'm going to write down Big Chalupa. And fill in my numbers then. So D is what? D is equal to VI, which is 0, times T, which is 2.5, plus 1/2 times 9.8 times 2.5 squared. Now remember, we've seen this before. If you have a term that's got a 0 in it, that 0 means the whole term is going to be 0, so I can simplify this by saying since that term has a 0 in it, the whole term is going to go away. On my calculator, all I have to do is 1/2 times 9.8 times 2.5 squared. I'm getting 30.625. 2 decimal points would be 30.63. What does that mean? Physically, what I just found is I found this height, right? How high the bird is from the ground. Now, the other thing I do, actually, you don't necessarily have to label it in the picture, but there is one thing that I do recommend that you do, because sometimes the answer to earlier parts of the problem are relevant later on. So usually when I get an answer, I add it up here to my T-chart so that I have it if I need it later on. All right. Part B, how far across the ground did the coconut travel? All right, first of all, 10 seconds to tell someone in your group. How far, or is this an X question or a Y question? If I want to know how far it traveled across the ground, is it an X question or a Y question? 10 seconds to tell your group. And if you told your group that it's how far across the ground is an X dimension question, then you were correct. So I want to find the X, and if it's how far, I'm once again looking for distance. So funny enough, if I want to find the X distance with VI, T, and A, if I pick my equation, I'm going to find it's actually the same equation. It's the same equation. I'm just going to plug different numbers into it. So this time I'm plugging in my X numbers. D equals 11 times 2.5 plus 1/2. Now be careful because a lot of times I see people plug in 9.8 for the A. Oh no, we're looking in the X direction now. In the X direction, the A is 0. And because there's a 0 in this term, I can cross the whole term out. So on my calculator, all I need to do is 11 times 2.5, which I am getting to be 27.5 meters. And again, like usual, like I did the last time, I'm going to add that to my list up here. And physically, by the way, what does that mean? Physically, that's this distance, right? Is 27.5. I just want to stop for a second because this is a lot of math, and it's easy to get lost in the math here. But I want you to realize what you've done, right? You take two numbers. I gave you two numbers: 11 meters per second, 2.5 seconds, and from that you were able to determine how high the bird was and how far the coconut went. Now remember what we said in the history of science. Who were the first people who were interested in understanding projectiles? They were the soldiers who were firing cannons, right? And why did they want to fire cannons? They want to know if they fire a cannonball and they know how fast they're launching the cannonball. They want to know where is it going to land. Well, you can kind of see, we haven't gotten to a cannonball question yet, and we won't till next week, but you can kind of see where a solution to that is coming from, because if you've got a speed, right, from there, and in this case from the time, we were able to find how far this coconut fell. So you can kind of see, if we take this reasoning farther, we'll eventually be able to predict the location of a fire cannon. All right, part D. What is the x and the y velocity of the coconut just before hitting the ground? So now what we're saying is we're going to let this coconut fall until it's right here. And the moment before it hits the ground, what is the x and the y velocity? So these are at the final, right? And it's kind of asking two different questions here. So I'm going to divide this in half. I have two different questions. I have an x question and a y question. The question is, what is the final velocity here? What is the final velocity here? All right. I'm going to give you a minute to do that. So for the x1, you're going to use the x knowns and unknowns. For the y one, you're going to use the y knowns and unknowns. I'm going to have Mrs. Taylor pause the video here for, say, 3 minutes or so, and see if you can calculate these two answers. So hopefully you found, so now we're back after the pause, hopefully you found that the best thing to use in this case, it's not the only thing you could use, there's actually more than one way to solve this, but I think the easiest way to solve it is Old Faithful twice. So VF is going to be equal to VI, which is 11, here I'm going to zoom in so you can see a little better, 11 plus the x acceleration, which is 0 times 2.5, which comes out to be 11 meters per second. Is that surprising? Well, hopefully it's not surprising, because as we've talked about before, the velocity in the x direction is constant. So if the initial velocity was 11, the final velocity better be 11. And then let's look here. So here, for in the y direction, my initial velocity is 0. My acceleration is 9.8. My time is 2.5. If I plug that in, I'm getting 24.5 meters per second for the final velocity. And we're going to bring it all together in part E. What is the magnitude and direction of the resultant velocity just before hitting the ground? All right, so what do I mean by that? So what I found is these are the two components. So if you go back to our diagram here, we had a coconut that initially was traveling this direction. The moment right before it hits the ground, think about which way it's going. Right? It's kind of going in that direction. Well, that's a vector that's pointing at an angle. What do we call vectors that point at an angle? They're called resultants. Right? And whenever you have a resultant, you can draw an x direction and y direction. My diagram's getting a little messy up here, so I'm going to redraw that up here. So my final velocity vector, my resultant final velocity, which I might call final velocity r for the final velocity resultant, has a final velocity x and a final velocity y. And we found them, right? The final velocity x is 11. The final velocity y is 24.5. All right, time to go to your notebook. Type 1 or type 2? 10 seconds to tell your partner, type 1 or type 2. Hopefully you found that it was type 1. Why? Because I know Vx and Vy. So I need to find two things. I need to find the Vr, that's the magnitude. And I need to find theta, that's the angle. So we're going to write down our two type 2 equations. This one, Vx squared plus Vy squared equals Vr squared, and the angle is the inverse tangent of Vy over Vx. Once again, I'm going to have Mrs. Taylor pause the video for about 3 minutes while you solve that. And if you have trouble, if you don't remember how to put this in your calculator, please ask. Ms. Taylor knows how to use tangent on your calculator, so if you forget how to do this, please ask. So hopefully you got something like this, 26.86 meters per second, 65.82 meters. Remember, you can kind of combine those two answers together like this. You can say that the final velocity vector is equal to 26.86 meters per second at 65.82 meters, or sorry, degrees. So, oh yeah, what does this mean? What that means is, what is the coconut doing? Right now, it's going this way at 26.86 meters per second. And what is that direction? Well, that direction is if I were to go horizontally and I were to go 65 degrees below that, that's the direction it's going. All right. Let's try one more. A plane is flying 30 meters above the ground. A package is dropped from the plane and travels 50 meters horizontally before finally striking the ground. All right. So again, I'm not going to bother drawing an airplane because again, art is not the point. The point is getting the point across. The point is I just want to see the projectile and the path it's going to take. So if the box is in an airplane, and it does say I'm going to assume the plane is going horizontally. So I'm going to assume the plane's going this way. So if it drops the box, right, the way the box is going to go is once again that curve. And I know that the airplane is 30 meters above the ground and that the package travels 50 meters. So that's what I know from the problem. Now we're going to do our XYT chart. Here's what I'd like you to do. We're going to pause the video again for a few minutes, and with your group I want you to see how many knowns and unknowns you can get. My hint is there are 5. Now if you can't figure out all 5 of them, there are at least 2 of them that are right there in the problem, and there are another 2 of them that we said are always true. But see if you can see if you can get up to 5 knowns in this T-chart, and we'll pause the video here. All right, let's see what we got. So, what are the 2 things we always know? Well, we always know that the x acceleration is 0. And we always know that the y acceleration is some form of 9.8. We have to decide whether we want it to be positive or negative. Just to try something different this time, I'm going to make down be a negative number. Just to try something different. You don't have to do it that way. You just have to be consistent on the problem. All right, what else do I know? Well, I know 30 and 50. 50 goes in this direction, which is the x direction. So that's my x distance. 30 is in my y direction, so that's my y distance. But I have to be careful because the box actually doesn't travel 30. Since I've said that down is negative here, right, the box actually travels downward, so negative 30 meters. I wonder if anyone found the last hidden thing that you know, which is that this box starts at the top of its motion, and what do I know about the top of its motion? At the top of the motion, Vy is 0. So that's here at the beginning, so I'm going to call that the initial velocity in the y direction is 0. Those are the 5 things we know. All right, now part B. How long did it take the package to hit the ground? Well, time, think about the last problem. Did we say time was an x number or a y number? Well, if you recall, we said that time is a scalar. It doesn't have direction, so you can put that number on both sides. So what that means is I can decide whether I want to approach this as an x problem or a y problem. But if you look at the knowns and unknowns that I'm giving, you should see that it's going to be easier to approach this if I treat it as a y problem, because I know more y numbers. So here I would say we're going to treat this as a y problem. How long did it take to hit the ground? Find t. All right. Look at the board. Pick an equation. We're going to pause it for 3 minutes to pick an equation using y numbers to try and find the time. So again, pause the video for 3 minutes. All right, you should have seen that you want to use Big Chalupa. So I'm going to plug that in there. D, negative 30, equals VI, which is 0t plus 1/2 times negative 9.8 times t squared. Now, luckily, once again, we have something that's 0, so it can go away. So if I rewrite this, I'm going to have negative 30 equals half of negative 9.8 is negative 4.9 t squared. Get rid of the 4.9. Negative 30 divided by negative 4.9 is 6.12, but that is t squared, so the last thing I got to do is undo the square. And I've got something like 2.47 seconds. That's what I found. Now remember, a time, when you get a time is the same on both sides. So now that I know that, I'm actually going to write it as in the y direction where I solved it. But sometimes I call the time the bridge variable because it's the one variable that connects the two dimensions together. So if it's 2.47 here, time is also 2.47 in the x direction. All right, part C. How fast must the plane have been flying? Well, we already kind of indicated here that the plane and the box that was on the plane was starting out moving horizontally. That means that this is an x question that I have to solve. Now, if I want to find a velocity, is it a VI or a VF? Well, think about when was the box on the plane. The box was on the plane up here, right? So VI is what I'm looking for. Pause for 3 minutes. See if you can use your x numbers to pick an equation and solve. You should see that it's the same equation again. It's Big Chalupa again, but this time using x numbers. So D50 equals VI times my t, which is 2.47, plus 1/2 times 0 times 2.47 squared. The 0 cancels out. So I solve this by dividing both sides by 2.47. If I did this right, we should be getting that the initial velocity is 20.24 meters per second. And I will go ahead and add that up here. D and E are just like they were on the back. So I'm going to have you do D and E on your own. When you're finished, this needs to be turned in by the end of class today with D and E done. If you're stuck, here are the things you can do. Number 1, you can look and follow what we did on this side. Number 2, you can talk to your group members. See if you can get some help from your group members. Number 3, you can raise your hand and ask for help. But I would would like you to attempt Part D and Part E. And like I said, I'm going to collect that. I'm going to have you turn that in. And I will look at that when I return tomorrow. All right, thank you guys for your good work today. Please continue to be on your best behavior while I'm not here, and I will see you tomorrow.